In this video, I will describe how to put deep learning inside iterative image reconstruction, and I'll be using PyTorch in order to achieve that. So let's get started with a motivating demo to show where we're headed. What we're going to be seeing and what we're going to be coding up is the following, where what I'm about to show on the screen is an iterative image reconstruction algorithm known as MLEM. I refer you to other videos to understand this algorithm, but very briefly, in the top left corner here, I have a true object, an image if you like, and in the bottom left corner here, I've got a reconstruction of that, which has been iteratively found after just 2 updates. What's happening is that this image here, I'm calling it X, is forward projected, is compared here with the measured data. This is the measured data corresponding to that top left true object. So the reconstructed image is forward projected, compared with the actual measured data, and we take a ratio between that measured data and the forward projected data. There's the ratio in the top right corner. This is back project, and then used to multiply, and there's a sensitivity image as well during that multiplicative process. So this is the well-known iterative algorithm, and what we're going to do in this video is put deep learning inside this, in this case for the purposes of acceleration. And what we'll be doing is training it up with a very simple single training pair of data in order to achieve the following. Let me just show you what we'll be doing. There I'm putting a copy of the reference reconstruction that we've just seen in the bottom left corner. I've copied it there. But now look at the bottom left here. We can see that we've got a very differently processed reconstructed image. What I've done is embed a convolutional neural network inside the iterative loop of this reconstruction algorithm. And you can see that because I'm training that CNN in such a way as to deliver a high quality output that matches the ground truth, we can see that the iterative algorithm is delivering a much improved image compared to the simple 2 updates that we previously saw. But this will become clearer as we go through the slides and the code during this video. So let me just interrupt this and let's get underway with the code. So first of all then, I'm going to use the scikit image library data to import that CT brain phantom that you've just seen on the screen. Also, we're going to need our essential imports. I'll show a few of them in the following copy here, where what I'm going to be using, of course, is NumPy for a few basic calculations. I'm going to import Torch. We need that deep learning framework, as well as this module NN, which provides us with opportunity to create neural networks, convolutional layers, and so on. We'll get into that presently. And also I'm going to use OpenCV in order to do a very quick image update. And so straight away then, I'll quickly go over my display function that you've just seen in those earlier demos. I'm calling it CV2 display. It just takes a named window. I supply an image, specify the X and Y position of the window. I also specify a scale factor to make the image larger for nice clear display purposes. And then basically what I'm doing is using cv2.imshow. So this is a function that comes with OpenCV when you import CV2. And I'm just going to put the image in that named window, and I'm just going to resize that image so that it's nice and big according to this scale factor here. Okay, and when I do the rescaling, I'll show you where I get that function from in a moment. I'm just going to do nearest neighbor, so no special interpolation on the display. And for the display purposes, I do need to just normalize the supplied image, which is IMA, such that its maximum value is equal to 1. And then I'll just simply move the window to position X and Y, XP, YP on the screen. So this is my kind of one-liner function for doing a very fast image display, which we'll need as we go along to check how things are progressing. Now that display does use a rescale function there, and I'm taking that again from the scikit image library, where I'm going to be using rescale, and later on we'll use resize as well. Okay, so that's kind of like the very basics. Let's now maybe take a look at setting up that true object, just so as we can see where we're headed. And so the brain image that we'll be dealing with in this demo is just simply the one from the scikit image library there. And I'm going to call that the true object as a NumPy array. Okay, We're going to need to use torch tensor variables when we come to the machine learning for the deep learning. But of course, we always start out with often with NumPy arrays. And so that's what we're doing here when we read in that brain object. So basically, I'm taking slice 5, and then I'm just taking a subpart of the 2D image, that is that CT slice of the brain. And I'm going to specify that I want that to be a particular size that we'll use in our demo. And so I'm going to use number of samples in the X dimension. I'm going to set that equal to 128 samples. Okay, and so this is just getting us underway with defining the ground truth. So what we can do already then is take a look at the true object just to make sure that, that we've loaded that in correctly. So I'm just using my quick display function there, labeling that as the true object. And of course, it's just that NumPy array. I'm going to position it at the top left corner, so 0, 0, top left corner of my display. And I'm going to use a certain display scaling factor. And so to make those images nice and large on the screen, I'm going to have a scale factor of 4 when I do my displays. Okay, so that'll just multiply 128 by 4. Okay, so also to take a look at the image, I'm going to need to wait for a key press, so it actually stays on the screen. So I'll just quickly set that cv2.waitKey 0. That just waits for a key press. So let's just quickly check that what we've coded so far does indeed show a true image. So this is the code we're currently writing here. And let me just run that, make sure it works. And there we can see the top left corner is that true CT slice that we'll be using for the demo that you saw earlier, which we're about to now code up. Okay, so I'll also quickly take you through a few slides that you're going to need to understand what we're going to be doing. So let me just pull up these slides here. So this is the algorithm that we're going to be using, the iterative image reconstruction algorithm. Basically, we have an image X, we forward project it, we do a ratio of the measured data to the forward projection, back project it using the transpose of this matrix A, multiply it by the current image estimate to get the next one, and we need to divide by A transpose 1. That just is a sensitivity image, just a back projection of a unit sinogram. So as a computational graph, if you like, what we can do is unroll this iterative algorithm into the following series of operations. So we have an initial starting estimate of the image. We put it into this EM update formula, which I've got on the top of the screen here. And we just keep repeating this process of forward projection, ratio, back project, and multiply, and of course the sensitivity image. And we just keep doing that iteratively until we end up with some endpoint iteration. Now in the simple example I showed earlier, we only had done 2 iterations, and so that's why this is quite a blurred image. And of course, if the measured sinogram data had been noisy, after many iterations, we'd end up with a noisy reconstruction. Now, what we're going to be doing in this video and in the code I'm about to take you through is a very simple way, rather intuitive, but the more sophisticated methods will still need the same kind of approaches that I'm doing here. Here, what I'm going to do is just put a convolutional neural network in between each one of those EM updates. So it's an inter-update convolutional neural network mapping, and I'll be training that CNN mapping such that the endpoint iteration, and in this simple example, we're only going to use 2 EM updates, but we'll train an inter-update CNN such that that last iteration agrees with the ground truth. Now, of course, if you don't have a ground truth reference, what you could do instead is train up to match some higher quality data, higher count data, for example, in the case of PET imaging, or more fully sampled data in the case of other imaging modalities. So what we've got then is an initial input image. We're reconstructing this sinogram M from the sinogram M by doing this EM update. We get some output, and then what we're going to do is put a CNN between the updates that will deliver an output that hopefully will match the desired high quality target image. And we're going to use a mean square error loss function. Now, to do this in PyTorch, when we go through our forward our computation graph here, our forward modeling here, when we go through all of that, what we need to do is to compute a loss, the mean square error loss between our output and the target. And then what we need to do is take the gradients of those of the loss function and update the parameters of our CNN, which will be the same CNN in every single update. Now, in order to do that back propagation of the gradients through our entire model, we're going to need to use torch tensors for the entirety of this calculation. And the slightly challenging part there is the system model A, which does, for example, in this simple example, just does the process of forward projection. So we're going to need to put that matrix A into a PyTorch tensor, and that is what I'll be showing you. So here I'm just showing what the matrix A typically does. It's just a collection of parallel line integrals through the object to project it to deliver a sinogram. That's what that linear operator, that matrix A, does, and we need to code that up and put it into a PyTorch tensor. Okay, so this is what we're about to code up now. In PyTorch, we're going to do this forward projection method, where what we do is consider every single pixel in a 2D image. So here, you've got to imagine the 2D image is in this XY plane, and we're just visiting pixels in this XY plane. And then for each pixel, which is a given XY position, we just project it to this parallel projection here for a given azimuthal angle phi. So I'll take you through the code of that, but if you do the mathematics of this simple process of considering any point xy in this plane, and when you see where it projects to along angle phi on this projection, what we'll be doing is calculating a kind of a radial position, which I'm calling y prime, of the projection. And so this is how we take an xy pixel coordinate for a viewing angle phi and project it to a radial coordinate on a sinogram, which I'll be calling y prime. Okay, so let's get into coding that up. And so what we'll need then is to create that system model A as a system matrix. Okay, so this is my code for that. What I'm doing is saying I want to be able to make that matrix A a torch system matrix, and it's going to be driven by how many samples I have in the image in the x and y directions, which is nxd, so that's the number of samples in x and y. And then we're going to need the number of radial samples on the sinogram that we're projecting to, so that was that sinogram M that we saw earlier. And we're also going to need to specify how many projection angles there are. And then the system matrix is just simply going to be a very large matrix where each one of the columns corresponds to a projection, the sinogram, in fact the whole sinogram, of a given single pixel. And so maybe I can show you that graphically as well, just to hopefully consolidate that. So here's an image X, and so here I'm showing if the image X is just empty except for a point source located there. What we can do is forward project that, and that's going to give us a sine wave or a sinogram corresponding to that point source. And when we devise this system matrix A, this forward operator, what we're doing effectively is treating this image X as a single vector. If you like, we've unrolled this 2D image into a column vector here, X. And likewise, the forward projection of that point to a sine wave, a sinogram there, we're going to take that 2D sinogram array and also unroll that or flatten that into a tall column vector, which means that when we consider all of the different point source locations, so there are of course nxd by nxd positions that we're considering in the input image, then we're going to have nxd by nxd possible columns, okay, and then each one of those columns corresponds to a sinogram according to the location of the point source. So I do cover this in other videos which you can look at if you need more information on this. We need to focus here on the code and that's what we're doing here. So to create that system matrix A, what we're going to do is step through X pixel locations and Y pixel locations, and we know we've got NXD and NXD number of samples in each one of those. So now we've got a selected pixel. Here I'm calling it XV, if you like, a voxel, and Y, X and Y voxel coordinates, pixel coordinates. And then for each one of those pixels, we then look at the projection angle phi, and we've got n phi number of different projection angles, and then we simply calculate what is the projection of that xy pixel location onto a 1D parallel projection at angle phi. And so this is the formula that I briefly put up earlier. We're basically saying it's xv times sine phi plus yv times cos phi. Now all I've done here is just correct for the fact that we basically got n phi samples and we need those to go between 0 and pi. So therefore I'm doing pi divided by the number of samples, and ph is the current index of my projection angle. And so the same for the sine here, the argument of that. And then also the x and y pixels count from 0 to nxd minus 1, but I need to consider a proper origin in the middle of my image, so therefore I subtract off half the number of the samples in the x dimension and in the y dimension. So that's why I'm just correcting the x and y coordinates. Now here, yeah, that would correspond to exactly the center of the array. And then when I've calculated y prime, the radial coordinate, the projection, the radial coordinate on the 1D parallel projection, I can then look at the bin of the sinogram that's corresponding to just by adding on NRD divided by 2, where NRD is the number of radial samples. And so long story short, that allows us to find to access a location in that huge matrix A that I showed you earlier. It allows us to access a particular index in that matrix and put in a value of 1, showing that pixel X and Y impacts upon that location in the system matrix. Maybe to illustrate that further, I could show you this slide here. So that matrix A that I'm just creating will have the following form, where what we're going to do is step through all of the X and Y positions, which correspond to all the columns of the matrix A. And for each column, what we're doing is finding a sinogram response for that point source. So in this figure, I just want you to focus on the sinograms. In other words, we're doing a column-based understanding, a pixel-driven forward model of the system matrix A. If you're doing a row-based, then we'd be looking at the line integrals, but these are completely equivalent, and I just want you to focus on the column-based understanding in this work. Right, so that's talking you through the system matrix. Maybe one other thing to point out here is that because we only have, of course, one row index and one column index, and we're dealing with 2D coordinates in the sinogram, 2D coordinates in the image, all we need to do is convert those coordinates to a single index, and so this is just the conventional way of converting a 2D coordinate to a 1D index for the rows, or a 1D index for the columns of this large system matrix. Again, this is in other videos which you're very welcome, of course, to check to understand how to build a system matrix. But there it is as a torch tensor, which is what we're going to need when we want to do deep learning in iterative reconstruction. We need to be able to basically back propagate gradients through our sequence of EM updates and CNNs with trainable parameters. Right, so let's now use that system matrix to forward project a true object. And also we're going to need to be able to back project, which is applying the transpose of that system model. So here are my functions for forward projection and for back projection. So with forward projection, I just take an image and I supply a system matrix. I also specify the dimensions here. So that's the number of X and Y pixels. the number of radial coordinates on the sinogram, the number of azimuthal viewing angles on the sinogram. And then to do a forward projection, this is where the benefit of using a system matrix comes in. All I've got to do is do a matrix vector multiplication between my system matrix A and my image when it has been reshaped as a column vector. Okay, you've seen that earlier. We take a 2D image, flatten it to a column vector, then we can plug it into the system matrix and get a column vector as the output. And of course, when we do a forward projection, we actually expect a sinogram, which is why we need to then reshape that column vector output into a sinogram, which of course in my notation has n phi, number of azimuthal viewing angles, n phi rows, and number of radial coordinates, radial bins, nrd columns. And so back projection is just the transpose of that operation. So the dot t there for the transpose operator, and it just operates on a sinogram. Right, so we've done a lot of hard work here. Now let's actually take a look at applying those forward and back projections to our image. What I'm going to do first of all is actually make the system matrix. At the moment I've just been defining functions. So now let's actually call up that function. And what I'm going to do is specify the number of pixels in X and Y, the number of radial bins in the sinogram, and the number of azimuthal viewing angles. And I'm going to make that system matrix. And also I'm going to crucially put it on GPU memory. But given that we might not always have a GPU to hand, what we're going to do is specify the device, which could either be our GPU if we've got one, or else it would default to a CPU. So this is a nice general way of working according to whatever environment we have. Right, okay, so having run those, what we can do is go ahead and use the forward projection now. So this is going to be finding a true sinogram, and of course we're doing the system matrix as a torch tensor, and so it needs to operate on a torch tensor. So we're going to need a true object as a torch tensor. Now remember earlier we had a true object as a NumPy array. So what I'm going to need to do is convert that NumPy array here. I need to convert that to a torch tensor. And so I'm going to use a function, which I'll describe in a moment, which converts a NumPy array to a torch tensor. So let me show you the code for that. I'll put that at the top here. This is quite an important function. So this is going to take a NumPy array and convert it to a torch tensor. So this is the from NumPy, and also what it's going to do is convert it crucially also to a 4D array. And the reason for that is that when we use convolutional neural networks, we're actually going to typically use 4 dimensions. The first dimension is the batch. Second dimension is the number of channels, and then the next 2 dimensions are our 2 spatial dimensions. So what I need to be able to do here is easily convert from a 2D NumPy array to this 4D torch array, which can pass nicely through a convolutional neural network. Also, while I'm at it, let me also describe the opposite process, because often once we've done our neural networks and so on, we're going to want to be able to visualize the outputs, and so then we're going to need to take a torch tensor and convert it to a NumPy array so that we can actually visualize whether it's matplotlib or whether it's my CV2 display function here. These are going to use NumPy arrays. So what we're going to do is take our torch array, our torch tensor if you like really, it's going to detach it from the computational graph, make sure it's on the CPU, and also express it as a NumPy, convert it to a NumPy array. The squeeze here is just going to remove those extra 2 empty dimensions that would have been created, for example, by that function there. So this is quite crucial when we're using PyTorch. We're going to need to be able to swap to and fro between torch tensors and NumPy arrays. Okay, so hopefully we can begin to see some of the benefits of all of this effort so far. So remember then what we've done back here. We had defined a true object, that's the CT slice that we saw earlier. I've then converted it to a torch tensor. I've then created a system matrix A, and then I've got forward and back projection functions. So what we're going to do then is, having made the system matrix, we're now going to use that system matrix to forward project that true object. Okay, so that's going to give us a true sinogram as a torch tensor. So let's now take a look to see the result of that. So now I can use my CV2 display function to take the true sinogram, that torch array, convert it to a NumPy array, and then just display it on the screen at, this is the X position of the window, that's the Y position of the window, and my display scale as mentioned earlier. So now we should be able to see not only the true, but also a true sinogram. So let's see if that functions. This may take a couple of moments to run if there are no errors. Okay, there is a problem here. Device is not defined. Okay, so I'm going to need to make sure that I've put the device definition sufficiently early on. Okay, so this is where I clearly need to have that, because this true object torch is defined on the GPU if we have one. So therefore I'm going to need to be aware of what my device is much earlier on in the code. So that's solved that problem there. Hopefully, let's check that this now compiles. Okay, now we need to also, it's saying it doesn't know what NRD is. Well, NRD is our number of radial bins. So remember, we've got 128 pixels in the X and also in the Y direction. For NRD, I'm going to use the following definition. So what I'm going to do is, because if you think about taking parallel line integrals for all the different projection angles at 45 degrees, we're going to have root 2 times the length of the number of samples. So in other words, the largest that can be, if we want to consider all of the pixels at any given projection angle, at the worst case of 45 degrees, we're going to need at least 1.41 plus times the amount of the number of samples in the X dimension. So therefore I'm going to define the number of radial bins as root 2, here I'm rounding it up to make sure we definitely capture everything, root 2 times the number of samples in the X dimension. So that's defining NRD. No doubt we're also going to need to define the number of azimuthal viewing angles, and I'm just going to set that simply to be the number of pixels as well. So hopefully now this code will run without error. Let me just see if that now runs. Okay, we're still struggling a bit because actually it should be N-phi is what we're using here. Let me check that. That looks correct now. Sorry for that slight delay. We should get this functioning any second now, and it's looking more promising. Top left should be the true CT slice, and then that delay was because it was calculating the system matrix as a torch tensor, and then remember we used our forward projection function to generate a sinogram, and that's exactly what we see on the screen here. Now this is a very crude nearest neighbor forward projection, but you know, feel free to take it a step further and do interpolation. So this is our true object, this is our true sinogram. Okay. So a lot of the hard work has been done now. Let's begin to get on with the iterative reconstruction and also putting the CNN in. Okay, so for the iterative reconstruction, remember that slide I showed you earlier where I was emphasizing that we need to do this as a computational graph. There's our iterative algorithm, and what we're viewing that as is an unrolled cascade of EM updates, and we're going to be putting a CNN in between them. So this is like a computational graph, if you like. We take some input, we run it through a series of operations, and we get an output. So to do that in PyTorch, that's like a PyTorch model, we're going to be creating a class, okay? Now, at the core of that class will be our iterative algorithm. So what I'm going to do is just paste this into the editor here, and I'll talk you through exactly what is going on. So this is our network for MLEM with no trainable parameters. First of all, in anticipation that we will be putting a CNN into this, I'm just going to pick up the torch.nn, the neural network base class that is used for all PyTorch neural network modules. Then we're going to need to be able to initialize this class when we instantiate it as an object. And when we initialize, we're going to be specifying the sinogram that we're going to reconstruct from. And we're also going to say how many iterations in it. In other words, how many of those unrolled iterations we're going to be using. Okay, so that's the definition of the initialization when we're going to instantiate this as a function, as an object. And then we're also going to need to run the initialization from the torch.nn module. So that's just like a standard requirement, because again, where we're going is that later on, we want to be able to put a CNN inside this MLEM. The other thing we're going to be doing at this stage with the initialization function here is just specify the number of iterations, which is going to be passed as an argument during initialization. And then also just as initial variables that are going to, attributes, if you like, of this class that are going to remain fixed actually in this EM algorithm. What we're going to do is define a sinogram filled with ones. Remember, in the reconstruction algorithm, we need A transpose 1. And then we're going to back project. In other words, the sinogram of ones is just the vector of 1 that you would have seen earlier. I can just put that back up on the screen. There's the vector of ones. And what we're going to do is do A transpose on that to get the so-called sensitivity image. So that's what I'm doing here. I'm just back projecting. So it's A transpose operating on a sinogram filled with ones, and the sinogram filled with ones is just a torch array that is just like the sinogram we're going to reconstruct from, except it's just filled with ones. There's the back projection function. Okay, so that's the initialization for what we would normally do if we initialize an iterative image reconstruction such as MLEM. Now, this class definition for the PyTorch model, the core part of it, when we call it up, when we run it, it's going to use this forward method, this forward function, where we supply the sinogram for reconstruction. What's going to happen with that computational graph? Well, first of all, remember we have some initial image, and for MLEM, that's just an array filled with ones, where we've got NXD pixels, it's just filled with ones, and that's going to be our reconstructed image. And what we're going to do then is iteratively update that. So that's the series of code here. Let me show you again what we're about to do there using this presentation. So what we're going to do is there's the initial image filled with ones. We're going to run it through this EM update, which means forward project, ratio, back project, multiply, which is that equation there. And that's exactly what we're doing in this loop here. We're just doing a for loop with iteration number IT, given by the number of iterations that were specified at initialization. And we're just going to forward project our reconstruction using the system matrix A. We're going to take the ratio based on M, the sinogram we're reconstructing from, divided by the forward projection, which is AXK. So that's the forward projection just done there. And I've just got a safety offset in here to prevent division by small numbers. Then we do A transpose, the back projection of that ratio. So that's back project using the system model as a torch tensor. Again, these are all torch tensors, which is really important because when we come to train this, when we build in trainable parameters, we're going to need to be able to back propagate gradients all the way through this computation graph. Okay, so there's the A transpose on that ratio. And then finally, we divide by A transpose 1, the sensitivity image. Again, I've got a little safety offset here. And once we've done that, we've got this multiplicative correction image, which can be used to multiply by the reconstruction to get an updated reconstruction. Now here, for visualization, I'm also going to be using my CV2 display. I'm going to convert these various torch tensors to NumPy arrays so that I can actually see them on the screen. I'm also going to print out the iteration number. And here I'm just using this as a millisecond delay in order for the windows to display the update. So one page there on the screen, if you like, is the entire PyTorch model. This one is not trainable for just MLEM as a neural network, as a deep cascade of operators just unrolled into a deep network. So that's what it looks like with no trainable parameters. Okay, so let's nonetheless use our PyTorch model with no trainable parameters at this point. And so to do that, I'm just going to, as they say, instantiate that network class, that PyTorch model, as an object and put it on the GPU if we've got one. If not, it'd be the CPU. It'll just be using CPU memory. And so what we do there then is just take our class definition, the name of it, MLEM net. It's going to take 2 initializations. Here we need the sinogram for the reconstruction. That's so as we can have the right dimensions for defining the sensitivity image, and then the number of iterations that we want. Here I'm defining a fixed number of iterations that I'll use later on as well. So I'm just defining that as 2, which is what we saw earlier in the intro. So we've now got DeepNet. Okay, that's an instantiation of that PyTorch model, that class. And that's something that we can treat, that object can be treated basically as a function that we can now supply a sinogram to, because if we call up that function DeepNet, we're basically looking at this forward method here in the class, which basically takes the sinogram for reconstruction. Okay, so all of that, I hope, will deliver an MLEM reconstruction. Let's see it. We've got visualization already built in. Let's make sure the code is all working. Let's run our latest version of the code. So there is going to be the true object. This is going to be to the right of it, the sinogram. Again, the delay is because it's making that system matrix. And there we go. It's now put up all the windows corresponding to what we saw at the very start of the video. There is the true object. Here is our reconstruction after 2 iterations. It was done very, very quickly. And in fact, maybe it's educational. We do that now. Let's do a much larger number of iterations, maybe 500, just to see if we can actually see that functioning, because we've got the display. So let's see if this will take us rapidly through, hopefully, 500 visible MLEM iterations. There we go. Hope you didn't miss that. That was pretty fast. It did 500 updates. Very rapid update. Feel free to check back on the video to see if you can see those 500 iterations unfold. This is the benefit of the very fast display. And there's the ratio sinogram virtually already set to 1s and the correction image virtually already at 1. But what we're going to do now is turn that MLEM iterative reconstruction into a trainable model by putting in a CNN, which in this case will be used rather sneakily to speed it up by only doing merely 2 modules. And then we'll use the CNN to do the very necessary corrections between updates to accelerate it. Now, of course, this is just for illustration purposes. You can use this kind of approach to build all kinds of models, such as forward-backward splitting EMNet, which I published with a colleague 2 or 3 years back now. So again, this video is just really to get you into understanding how to code up these computation graphs, these PyTorch models. Right, so there's the MLEM. Now, what I'm going to do is copy that. So hopefully, if you've understood all of that, I'm just going to copy it so there are no surprises. I'm just going to duplicate that now. There it is. There's a complete duplicate of it. But what I'll do is now I'll call it MLEM underscore. Let me just be consistent with my notation. I'm just going to call that MLEM underscore CNN underscore net, because I'm going to now put in a trainable convolutional neural network inside it. Now, before that, let me just display on the screen the reconstruction that was just found from that previous MLEM network, which didn't train up, just 2 iterations. And what it's going to do is display, if you like, a reference point for a reconstruction. Okay. Then what we're going to need next is to define a convolutional neural network. Okay, so what I'm going to do is use one that I've done in a previous video. So to try and speed things up, I'm just going to copy and paste in, but I'll talk you through it briefly. A convolutional neural network, that's also a class which we're going to instantiate as an object, which we're going to train up. So basically, a bit like before, I won't repeat what I said before, but the core of it is using the NN module from PyTorch that allows us to use a series, a cascade of 2D convolutional layers. Here we've got one input image. Remember, we're doing this between MLEM updates. So we've got one input image, and then here I'm going to have 8 channels, which gives us 8 output images. And these are going to be convolved with 7x7 size kernels. With indeed, here they're going to have just one channel, but there'll be 8 of them. And we're going to need 0 padding to make sure that the size of the feature maps coming out of the layer is the same size as the input. And then by the next layer, we need now to operate on 8 channels that have come out from the previous convolutional layer. And we'll have 8 channels again for these 8 kernels. So we're going to have 8 kernels that are going to have 8 channels. And again, the next layer, we're going to have 8 input channels, 8 output channels, and so on, all the way up to the last layer. And by the way, I've got nonlinear activation functions between these convolutional layers. Again, refer you to other videos for more detail. And so at the last convolutional layer, we're going to need to take 8 feature maps and just have one single kernel with 8 channels, such that basically those 8 feature maps are combined into one single output using a trainable 7x7 kernel. Okay, this is a convolutional neural network, and basically the forward method with that class is just simply taking X. Here we need to make sure it's a 4D torch tensor, so as we can use the CNN model here, these convolutional layers that need 4-dimensional torch tensors. So what we're going to do is just take X, a general X, unsqueeze it, make it that much larger, run it through the CNN. Then once we've run it through the CNN, we're going to then remove those excess dimensions and return a 2D torch tensor. So that's my CNN. And then, of course, we now need to put that in to our computational graph. Okay, but first of all, let's instantiate that CNN. Let's get that object. So this is going to say CNN is basically an instantiation of that CNN class as an object on hopefully a GPU. If not, it'll go to regular memory. Right, okay, so now what are the changes to get that CNN put into this class? Well, remember, all I've done now is just change the name of it. I'm also now going to need to supply that CNN instantiated function, if you like, that object. It's a class that's been instantiated as an object, if you like. So the CNN, I'm now going to pass as an initialization when I call up an instantiation of this new model with the CNN included. I'm going to need to include that CNN during initialization. Okay, and then we're going to need to keep that saved as well. So we'll do self.cnn is equal to CNN. So we keep hold of that CNN for this this class, for the object that will result. And then when we're doing our forward model, all I'm going to do is make use of that that CNN. And the way I'm going to do that, let me just copy the comment here as well so you can see exactly my description of it. I'm going to do an inter-update CNN where here the reconstruction is as before, but now what I'm effectively doing here is like a kind of a skip connection. I'm saying take the reconstruction and add on, so we'd still take the reconstruction, but now we add on a CNN modification of that reconstruction. And this CNN, defined back here, has got all these trainable parameters for those multi-channel kernels. Those values are going to be trained up such that that output ultimately will match what we want, that ground truth, but only over a couple or so iterations. Okay, so that's the key difference here, is just reconstruction plus some processed version of reconstruction will be the new reconstruction. Now, MLEM is a strictly positive or non-negative algorithm, and so I'm using an absolute on there to protect us from any negative values that might result. Okay, so that should now work. So what we'll do is we'll instantiate that model with the CNN embedded, and then why not go ahead and actually call it up. And let's see where this takes us. Obviously, we're not training yet. That's going to be the last stage for us to do. Okay, so it's now going to create that PyTorch, the torch tensor, that's the system matrix again. The true object's going to be there. There's the sinogram. Okay, right. So not much has happened at the moment because all we've done is run 2 iterations with an arbitrarily initialized CNN inter-update filter, if you like. Okay. Maybe what we could do to see if there's any major impact on that is actually use a large number of iterations there. We could change that to, let's do what I did before. Might as well, just for the quick demonstration here, let's do 500 iterations, rerun that, and then once we've taken a look at the output, because we just want to see what the impact is of that random CNN that's not yet trained, that's just been put between iterations for the EM update. So there's the regular MLEM. Okay, and oh, there we go, it's just counting all the way through. Now, okay, now it's using, and we can see what a disaster this is. This is not a trained CNN. We've got this rather unusual result. There's the reference MLEM with 500 iterations, and here is our new MLEM with a CNN not yet trained between updates. So quite a miserable result there. But now, of course, what we're going to do is train up that CNN such that the output of that cascade of operations actually corresponds to the ground truth reference. Now, for speed here of training and also to be consistent with the start of the video, I'm just going to use 2 updates, and so we're going to be using this as a way of accelerating a regular MLEM. Okay, so training, let's get on with that. This will be the last stage. We're nearly there now. We've only got a few lines of code to go, and so I'll copy all the remaining code across. It's not much left at all, and then hopefully we'll have a trained up inter-update, a CNN inter-update for MLEM. Right, let's talk about how we do the training. So, as you may recall, some time ago at the start of the video, I was talking about this slide here. So let's put that up again. What we're going to be doing is running an image through this cascade of operations, through this computational graph to get this output here. And we need that to match the high quality ground truth. And we're going to be using a mean square error loss function to see how well that corresponds to this. And so that's what we've got here. Our loss function is the mean square error loss. Now we're going to need a way of updating the parameters, okay? And so for that, we're going to use the Adam optimizer. So if you want to know more about that, there are of course many videos about the optimizers you can use to update parameters, but a simple understanding would be it's like a variation of gradient descent. Okay, and we specify a learning rate, a kind of step size for the update. Here I'm going to keep track of the training value, or rather the loss, in other words, the MSE loss between my input, or rather my current output, and my desired output, my label, my target. Here I'm going to train up for 2,500 iterations, and the training loop is very simple. We just take our sinogram, run it through our network there, the CNN MLEM network. That's what we did here when we ran it without training. And And that's going to give some reconstruction output. And then what we do is use our loss function to compare our output. Okay, that was what we saw earlier on the slide. And we're going to compare that to the desired true object, and that's going to be our loss. I'm going to save that in this train loss array here, this list basically. And then what we're going to do is find the gradients. Okay, so that's going to take the gradient of the loss function with respect to all the parameters of all the CNNs, the CNN kernels, all of the various filters, if you like, or the kernels inside that CNN that we talked about earlier. So it's going to find the gradients of the loss function with respect to the parameters. Once we've done that, we can then update the parameters. And then before we go around for another training loop, we need to zeroize the gradients, otherwise they'll accumulate, which is not what we're wanting. We're actually wanting to rerun the network, see the new output, compare it, you're using the loss function, update, zeroize the gradients, go through again, as I've just described. And so this will just run 2,500 epochs, report the training loss, and that is it. We should now be done. So let's take a look at the result here. Let's see if this does indeed train up, and we'll see it training live during the, we'll be seeing the updates as it does that training. Okay, so there we go. This is now doing 2 updates only, and you can see that this these 2 updates have got the CNN operating on them in between the 2 updates. So I found the cause of that flickering in the display, and it's simply because I am showing every single update in the process. You can see here that in my main iterative loop, I am displaying the reconstructions on each of the updates. And if we want a nice smoother display on what we're doing here, then what we can do is just display at the end of the computational graph only. So I could kind of just pull this back a level. So that means it will now do the unrolled network, and then only at the very output will it show us the updated reconstructions. So that would be a way, I believe, of resolving that flicker. It wasn't instability in the training. So the learning rate that I was using was actually fine. So let me just check that that now works. So I'm rerunning that exact same code that I've coded up, if you like, live during this video. And all I've done now is just change when I display those images. Okay, so there was the original MLEM PyTorch model. And then when I go to the CNN, you can now see that this is a far more stable, apparently stable update, because all I'm doing is now displaying the endpoint iteration after we've done the interupdate CNN. What we saw earlier with the flickering, that was because we were seeing every single updated image during computation. But if we just look at the endpoint, then we can get this far more stable looking reconstruction, where we see that this is indeed, instead of looking like merely 2 updates, courtesy of that trained CNN, that inter-update filter, we now have a far better looking image that corresponds nicely to what the training target is, which is the ground truth image in this case. So I hope this video has been useful as a way of demonstrating how to take, for example, a convolutional neural network and embed it within some chosen iterative image reconstruction algorithm. Thanks very much for listening.